Why do you know my name? No, I don't.
Okay, so hopefully you got a note sheet. Our next chapter we're going into is chapter 13. It is about solutions, which is what you were trying to find for Dunder Mifflin Company. So today, what you need to have due today is those fire suppression papers, those 4 pages right there, preferably in that order. Most preferably, because we like it that way. Make sure you turn it in though to your the teacher that observed the actual performance of your model. So even if you did it on Friday, it'd be with that teacher. If you did it on a separate day or something like that because you were gone or you had an excuse for doing it at a different time, it's with whoever actually watched it happen. So make sure you do that because really we have the pictures of them because we don't memorize every single person's model, so we'd have that to fall back on. So make sure you do that, please. Do by the end of the day today. Then for the rest of the day today, we're going to review mixtures. That's something from way back in the past. And then we're going to talk about the main thing, which is solutions, the next chapter we're going into. And then the biggest part of that is talking about concentrations of solutions. So that's what we're going to be doing today. Are there any questions about the pages? I'll give you a quick rundown again. Remember, the first page is your cover letter. Make sure you have your logo. Make sure you have both people's names if you're working with someone. What else are we going to say? Oh, only turn in one for your group. So if it's you and one other person, make sure you just turn in one of these. So that's all we need to get from you. So on that first page, make sure you have both your names on it. Make sure it's got a couple paragraphs. I would recommend going with 3 paragraphs, having like 1 paragraph kind of talking, thanking Dunder Mifflin for the opportunity to work with them and supply their needs for fire suppression. And then the next 2 paragraphs talking about what it is that you were able to accomplish with the model. And then always a good idea is to like say what kind of improvements would you continue to look forward to doing going on in the future if you get selected to do this. You might have a great project, but if you continue to give an idea of like, hey, I can do it even better and we can do more, that really says a lot to a company that you're willing to invest a lot into them. So definitely want to do that. The second page, remember, is the calculations. The first set of calculations you've already done. You should have turned those in with the preliminary plans that you had done. So that's the calculation for acid and baking soda for just the model. So you need to have that. You also need to have the calculation for the model with a 12 molar hydrochloric acid solution. So that would be another one that you're going to have. If you put that right with the other 2, that's perfectly fine. If you have that in a separate spot further down, that's okay too. But then the other calculations you need to have were for the amount of acid and baking soda for the actual large buildings in Iceland and Colombia. So you needed to do 2 separate ones for that. And remember, you got 2 different volumes because they had different pressures and temperatures. So make sure you accounted for that in your calculations. Then, of course, the last calculation is the fusion between carbon dioxide and halon. So that would be the one other equation that you needed to have solved for on that page. Third page is your inventory. Make sure you've got it totaled up, and let us know and kind of highlight whether or not you're below budget or above budget, where you are with that. And then the last page, of course, is your blueprints. Should look spectacular. So that's what we're hoping for. Any other questions about the paper? No, you guys are awesome. All right, so let's get started then. So if you take out your note sheets, we'll get going on our next chapter. So we're going to do kind of a quick review of some things in the past, going way back as it turns out. Hopefully you guys remembered when we were classifying matter and like trying to organize matter, kind of put matter in like a kind of hierarchy and connections, and what do we use, what are the characteristics that we use to look at different things and be able to know what kind of materials we're dealing with. Well, the 2 big categories were it was either a pure substance or it's a mixture. And mixtures are the most abundant. They're everywhere. I mean, the air you're breathing is a mixture. You yourself are a mixture. The food that you are going to eat is probably going to be a bunch of mixture of like spices and seasonings and things together. Very few things are going to be a pure substance that you're going to run into. But we can get pure substances out of mixtures because that's what goes into mixture, are substances that are mixed together, by using their properties to kind of separate them out, maybe their density or maybe your melting point and boiling point, stuff like that. So our substances that we could get out of mixtures are either compounds or elements. We can continue separating things down more and more and more. Eventually we get to our elements, which is the most basic form of matter we can get to. But we, of course, combine those elements together to make compounds which have their own unique properties as well. Considered them a pure substance, like water. Pure water is H2O. 2 parts hydrogen, 1 part oxygen, but it has its own properties that are different from the hydrogen and oxygen they came from. Then, of course, we look at mixtures, and we can separate mixtures into 2 big categories. And that was either heterogeneous or homogeneous. Anybody remember what's the difference between heterogeneous and homogeneous? How could you look at a mixture and say, I know that's heterogeneous, or I know that is homogeneous? It's really to look at it and be able to tell.
If there's stuff in it.
Yeah, if you can identify the parts that make it up. Yeah, if you can see the different components that are making up the mixture, that's heterogeneous. Homogeneous, it looks like it would almost look like it's a pure substance. It looks like it's the same thing everywhere within it. So, as an example, for a heterogeneous mixture, we got a salad. We're getting close to lunch. Hopefully not everybody's too hungry. We can see the lettuce that's in there. I can see some carrots and maybe some of that red cabbage that's in there. I can see the different components of that mixture. But if we had a different mixture like this guy, which is Kool-Aid, I can't see the sugar in there. I know there's sugar in there because that's what goes in. There's that little powder stuff you put in there. Where's the powder? It seems like it's gone. Did it melt? No. It's been dissolved. So homogeneous mixtures, they look the same all the way throughout. Heterogeneous, though, you can definitely spot and see those differences that are contained in it. So we have a couple of special heterogeneous mixtures we're going to talk about before we get to our special homogeneous mixture. First one's a solution or a suspension. Jumping ahead. Solution's a heterogeneous mixture, and here's the key thing is we look at the size of the particles that make up these mixtures. That's really kind of gives them their properties that we use to identify. A suspension's got pretty large particles, really large molecules or small chunks of bigger mixtures that have broken up into smaller pieces. The key thing for this is that the particles are so big that when you take a sample of this mixture, typically it'll look pretty much homogeneous at first, but after a little while, after not being stirred up and agitated, those particles start to settle out and you start to see different layers. You can definitely see, oh yeah, there's something else in there. There's definitely 2 different things that I can identify and point at, maybe even 4 or 5 or even more. Like an example would be this muddy water. At first it would look pretty uniform, pretty homogeneous, but after sitting for a while, because of river water gets churned up, there's that agitation that's going on. Like in environmental science, they call it turbidity, or how turbid is the water, how churny is it. And after a while, you can start seeing there's the particles. They're starting to settle out. They're just too big. They're like larger particles like silt and sand and clay and stuff like that. And they'll sit there at the bottom. And then you can definitely see, yeah, this is a different color than what's at the very bottom. I can start to identify the different parts that are in there. You could use a filter and collect that stuff. Whereas the liquidy part, that's not going to separate out into anything through a filter paper. Another good example is like children's Tylenol or pain reliever. That's an oral suspension. So you got to be kind of careful with that one. Make sure that you agitate it, you shake it up, you get it stirred up so that you get those particles redistributed throughout so you have kind of a uniform composition. Otherwise, if you're just taking off the top, you might not be getting enough of the medicine because all those the bigger particles are settled down at the bottom. And then if you continue to do that, eventually the bottom part's going to be too concentrated. You're going to get you give an overdose or something. Probably, hopefully not. But you have to be kind of aware of that. Juices are that way too. What do you have to do with a juice when you take it out of the refrigerator before you pour it out? Shake it up. Get it stirred up because you're going to have some larger particles that'll settle down because it has been sitting for a while and hasn't been stirred up. Colloid, this is one of my favorites. I love colloids. They're all over the place. It's also a heterogeneous mixture. These ones are sometimes tougher to identify though. A lot of colloids kind of look like they're homogeneous. Milk would be a good example. Milk really does look like it's the same material throughout and pretty much is if it's been treated to be kind of homogenized. If you look under a microscope, you can definitely see there's different fat globules that are floating around. Even in your skim milk, there's going to be a little bit. You're going to see those different components that are making it up. Blood is another good example. It looks at first like it's homogeneous, but yeah, after a while, if you're sitting, it's almost like a suspension. You can start to see different parts separating out. But a colloid, the particles are definitely a little smaller than what you find in a suspension. They won't settle out. They'll stay churned up. My favorite example is kind of think like a beach ball at like Lambeau Field. People blow them up and they'll like toss them around and people keep bouncing them and it keeps it up in the air until it gets down the field and the security takes it away. But it keeps moving around because there's something there to kind of bounce into and keep it moving. And that's what we have with the colloid. The material that these particles are mixed in with are moving around enough to kind of keep those particles moving. But they're still somewhat bigger than what you would find in a solution. But they're still smaller than what you find in a suspension because the suspension, they're too heavy. They would definitely fall out. So I've got an example here of a colloid and a solution, as it turns out. And we're going to try to compare them. You can kind of take a look and you can kind of see this one's a little bit cloudier than this one. But it's the cloudiness is pretty even throughout. So is that homogeneous or is that heterogeneous? I don't know. Well, to test that, we would scatter light or shine light through the mixture to see does the light be scattered out by the particles that are in there. If it's a solution, the particles are too small. They won't scatter the light. But if the particles are big enough, like in a colloid, they will scatter the light. So I'm going to try to do this. You guys are pretty easy because you're all nice and close to be able to see this. So I've got a laser beam. I shine it through and you can see it hit the wall. You don't see it until it hits the wall because that's where the light gets scattered finally. But as it's traveling through the air, you don't see the laser. So that should tell us, is air a colloid or is it a solution? Right, I can't see the light. Solution. Because if it scatters the light, then we know it's going to be a colloid. So air is a solution. You ever watch those movies like where somebody's breaking into the museum to steal a big precious jewel and they know that there's like some lasers around? What do they do to see the lasers? Spray something. They make a colloid, really. They make an aerosol. Aerosol is an example of a colloid. So then those particles are in the air and then the laser beam will show up. Now if we had like old chalkboard with like old erasers with some chalk particles in it, you could pound those chalk erasers and you get little particles, then when you shine the laser, you'd see it. You'd be able to see it throughout. Well, we can kind of do that with this guy right here. So I've got my solution here. The solution is just salt water. When I shine my laser through, you can see the light hit the edges of the beaker, but you really don't see the laser go through the water. Every once in a while you might see a little bit because there might be a little piece of dust or something in there that'll scatter it, but you really don't see anything there. But if this guy's a colloid and I shine my laser through, what should we see? We can see the beam go right through. It scatters the light out. What's that? Okay. Ta-da. There it is. So that's the Tyndall effect. So right here we can see you have a colloid on the right. It's just got a regular, like a flashlight beam going through, but we can see the beam because it's scattered out. As it goes through the solution over here, we don't see the beam going through because the particles are still too small for it to show up. Where does a colloid sometimes become a problem? Well, if you ever drive through some foggy conditions, you turn your headlights on, you have your headlights on high, you're going to get that scattering effect, the Tyndall effect, and you're not going to be able to see very much because the light gets reflected right away by the particles that are in the fog and kind of almost can blind you a little bit. So you can't see very far down the road, so you want to kind of use your low beams so the scattering is directed down, not back up towards your where you're trying to look out through the windshield. So we know a solution is not going to have that Tyndall effect because the particles are super small. And here's our definition for a solution. It's a homogeneous mixture. So this one's homogeneous. The other ones are considered heterogeneous. And it's a mixture of two or more substances in a single uniform phase. So that's what makes it homogeneous. It's the same throughout. The composition is kind of uniform within. Each spot's got its own similar concentration and same amounts of stuff located. So particles are really small: atoms, ions, molecules. And by molecules, I mean like really small molecules. Technically, this colloid I made it's got a molecule in it, but it's a really big molecule, starch. So yeah, these things are going to be way too tiny. Light's not going to be able to bounce off of them, be scattered out. So a couple of vocabulary terms. First one is soluble. Well, that one makes sense. Soluble means able to be dissolved. We were looking at chemical reactions. We were looking at, when we did a double replacement reaction, you take two solutions, mix them together, and you have the potential of things combining together that are not soluble. They were insoluble. They could not be dissolved. And those would be the precipitates that would eventually settle out, like a suspension. It would eventually drop down to the bottom. Solvent. That's the chemical that does the dissolving. So it dissolves chemicals into itself. It's not melting. That's the most common mistake people make. They think like sugar melted or the salt melted. It was dissolved. It was pulled into that material, that medium that dissolves it. And our last one is the solute. It's a substance that gets dissolved in the solution. Chemistry Cat says, why are chemists great for solving problems? Because they have all the solutions. Good old Chemistry Cat. Smart. All right, so let's take a look at what happens when something dissolves. Let's take a look at what happens when we have a solute and a solvent come in contact with each other. We're going to look at this one. This one's a video from Canada, so it's going to have some subtitles that are both in English and in French. So a little bit of multiculturalism going on. Sorry, Daniel's got it.
Come on.
I know, I was just... So here's how water dissolves in dissolved salt. So we got a water molecule here. So the water molecule has got that kind of teddy bear shape or Mickey Mouse kind of with a couple of big ears on the top there, kind of. A water molecule. Whoa, this giant thing just fell into the water. Oh, that's the salt. So if you remember, salt is an ionic compound, so you have those charges of positive, negatives, and they just kind of line up in all three directions, up, down, side to side, front to back, and that's what creates that salt crystal. So you have alternating sodium and chloride ions. Since water is a liquid and can flow, it's going to eventually bounce into it, and those water molecules are going to hit the salt crystal. And if you remember back to our polarity of molecules, water is a polar molecule because you've got that lopsided shape. It's that tetrahedron parent geometry, but you've got those two lone pairs that cause those hydrogens to be pushed to one side. So you end up with a positive charge on the hydrogens because they're lower in electronegativity than the oxygen. The oxygen is pulling those electrons away from the hydrogens and keeping it towards itself. So the oxygen side of this molecule is a negative, and the hydrogen side has got that positive charge. Because our salt molecules are charged as well, positive and negative, that's what's going to be the attraction. That's going to allow those water molecules to kind of grab a hold of ions and pull them apart. So we got the water molecule. Now here comes one salt particle. We've got the sodium ion is the red one, positively charged. And you got the chloride ion, which is the bigger blue one, which is negatively charged. All right, so here come the water molecules. Are going to come in. Notice that these ones are heading towards the blue chloride ion. And notice what side of the water molecules are all facing that chloride ion. It's the hydrogens, which are positively charged. The chloride is negative, so those opposites are attracting there. Eventually there's enough of a force and pull because there's enough water molecules to kind of start pulling that chloride ion away from the surrounding sodium ions. And eventually the water molecules win out, and they pull it right out and mix it in with the rest of the other water molecules. This time we've got sodium being pulled away because the negative sides of the water molecules were attracted. So the water molecules have surrounded both of them, but they do it oppositely. Here's the hydrogens, hydrogens, hydrogens are facing the chloride. Here the oxygen part is facing the sodium. And they surround it, and then they'll just carry it off with the rest of the other water molecules and eventually distribute those ions out evenly. It just takes an amount of time, and eventually enough water molecules will go in there, pull those ions apart, and the salt will completely fall apart. All those ions will separate. It's kind of like hyenas around a kill. They just grab their piece, they take off. All right. All right, let's take a look at an example of actual salt. So that was just a simulation. This is actual salt crystal under a microscope, and we're going to add some water to it, and the dissolving process is going to happen. We can't see the actual molecules and atoms at work, but you can kind of get an idea. It takes a little while before they add the water. And cue water. And it happens really quickly. You can start seeing it. It's just moving away. So that's just the water molecules themselves. They have that internal vibration and motion. They're bumping in and carrying ions away. Hold there. It doesn't take long, and it is gone. And given enough time, those ions will distribute evenly throughout. So you'll have the same amounts of chloride and sodium ions everywhere within that water. So it's just perfectly distributed after a while. It doesn't take very long. You can see how quickly those molecules and atoms can move around. All right, so a couple of examples of some solutions. Kool-Aid's already up there. So we have our saline solution. Anybody have contacts? Use saline solution? You ever get an IV? An IV is usually a saline solution. It also has some other things dissolved in it. But in this case, saline solution, our solvent is water. And our solute is salt. Typically it's about a 9% solution, or I shouldn't say 9%, 0.9% solution. So 99% of that solution is water, and then a little less than 1% of it is our salt dissolved in it. Kool-Aid, of course, our solvent is again water. Water is the big thing. We put the sugar and the Kool-Aid mix in, stir it all up, and delicious Kool-Aid. Here's another example. We've got a mixture. This is a solution. It's isopropyl alcohol, also known as rubbing alcohol. But in this case, the two things that are mixed are water and alcohol. Most people automatically think, oh, well, if it's got water, water's the solvent. Not in this case. The alcohol makes up 91% of this mixture right here, this solution. 91% is alcohol, only 9% is water. So that makes our solvent the alcohol, the more abundant chemical that is your solvent. But water is pretty commonly our solvent. We use that for a lot of our solutions that we use in chemistry because water is a really awesome solvent. In fact, we call it the universal solvent because it does dissolve a lot of things, but it doesn't dissolve everything. Because if it did, what would you keep it in? But it does dissolve a lot of ionic compounds and a lot of polar covalent compounds. That's especially the things that we're interested in, especially for living things. That's why we need water to be able to move a lot of those materials around because water will dissolve them. And the other reason is because water is pretty readily available on planet Earth. We got a whole bunch of water from running around. We can get access to it and be able to use it as our solvent. When you spill something on you in lab, you spill a chemical on you, what do? Rinse it out with lots of water because water is an awesome solvent. It tends to wash away most of the nastier things you would run into. So why are solutions so special? Why do we have a chapter called solutions and not a chapter called colloids or a chapter called suspensions? Well, the reason is because they're homogeneous. Having that perfect mixing of everything being perfectly distributed throughout the solvent. That's what makes them special. We can use them then and be able to control how much chemicals we have because we know everywhere throughout that mixture, that solution, I have the same kinds of amounts of things present. They mix so perfectly. So the same amount of Kool-Aid that I have here, that would taste just like the stuff down at the bottom. It took a while, but my youngest son just turned 10, and for his birthday party, he wanted to drink of my Mountain Dew, and he drank the whole thing. I said, "What?" I said, "Mom, the part I wanted was down at the bottom." So I had to drink through the rest of it. But it tasted the same. Oh, no. That's the beauty of solutions. They have the same makeup everywhere throughout. So if I have a big giant solution, and I only need a part of it, I know that I can take it from anywhere in there, I'm going to get the same conditions I would get anywhere else. Kool-Aid. Oh yeah. Any questions about why solutions are so special? I don't think there's a. So, what we're interested in is the chemicals that we dissolve into the solution, especially when we're dealing with water solution, aqueous solutions. We want to know what is that chemical we dissolve, how much of it is present. So there's some vague ways, some kind of generic, not real descriptive ways of saying like, well, that's a dilute solution. Well, that's a really concentrated solution. Because that tells us a little bit. A dilute means there's probably very little amount of solute dissolved. Concentrated, there's probably an awful lot of that solute dissolved. But in chemistry, we're always interested in numbers. We want to be able to say exactly how much there is, or have a really good definition as how much is there. When we do that, when we establish a number value for how much is present, we call that concentration. I always think of concentration as that one game where you had to put like little pegs in before the board popped open and everything went flying. I hated that game, so I was never good at it. Different kind of concentration. It's not thinking about something really hard. When we're going to do a chemical reaction with solutions, we need to know that concentration because we need to know the amount that's going to be available to react. We need to use that to be able to find out that we have a limiting reactant. We need to have that in order to do stoichiometry to figure out how much of a product can we make. So here, concentration, this is it. This is what we're going to be focused on. It's measured in moles of solute per liter of solution. It's got a special name. When it's moles of solute per liter of solution, that's molarity. And its symbol is a capital M. Sometimes it's italicized. But you see a big M. It's talking about chemicals dissolved. We're talking molarity. We've seen this. We saw this in the fire suppression project. We were using a 1.25 molarity concentration for our hydrochloric acid in the testing of a model. And then you had to calculate what it would be if you use a 12 molarity, 12 molar solution. And that's how that's pronounced. If you were to read off the number with the letter M, you'd say that as the M would be pronounced like molar. So you had a 1.25 molar solution of HCl, or a 12 molar solution of HCl. So, in terms of the actual, what it looks like mathematically, there it is, molarity, moles of solute divided by liters of solution. It's just a ratio of how much solute in the combination of the solute and solvent together making up the solution. So we can calculate concentration if we know how much solute we have, and we can measure the volume of that solution that we make with it. So this is an easy one. This doesn't get much easier than this one. We've got 4.8 moles of solute dissolved in 2 liters of solution. This is easy math. 4.8 over 2. So 4.8 moles divided by 2 liters, that's going to equal 2.4. And we would put an M after it, big capital M. And you would read that as it's a 2.4 molar solution. That's easy. That was easy. Are they always going to be this easy?
Yes.
I wish they were. Now we can complicate things, of course. Always can. So let's take a look at an example. We're going to complicate it a little bit. Not too bad, though. This is going to be a pretty easy one. So here we got a problem where what's the concentration of solution? That's 0.230 moles. So we know how many moles of our solute we have. Dissolved in 184 milliliters of solution. Well, in order to get concentration for molarity, we would need moles per liter. We don't have liters, though. We've got milliliters. But can we fix that?
Of course.
Yes, we can. We can have you Bobby go and fix that. First, we're going to change milliliters to liters. We could use a T-chart to do that, but we've already done that one a couple of times. So you know that it's just divide by 1,000 to go from milliliters to liters. So you're moving your decimal point 3 places to the left. So if you can make that conversion happen very quickly, very easily, go ahead and do 3 decimal places to the left to go from milliliters to liters. To go the other way, go from milliliters to liters, you want to move your decimal point 3 places the other way. So now we've got our solute 0.230 moles, and we have our solution volume in liters. So that's an easy one. Just plug that into your calculator. 1.25 molar solution. So nothing tricky here was the darn milliliters. Milliliters to liters, 3 decimal points to the left. Liters to milliliters, 3 decimal places to the right. All right, next problem. Let's see what we did to this one. What's the molarity of a solution? And this time we know the chemical. We know that it's sodium hydroxide. This isn't like any old chemical. Sodium hydroxide, where we have 14 grams of it dissolved in a half a liter of solution. Oh. So in this case, we've got the volume in liters. We're good there. There was no milliliters here. But what are we missing? We're missing moles. But we've been given this, 14 grams. Can we change grams into moles? Yeah, we can. So first we need to change our grams to moles. And where do we go to find that? Where do we go to do that? Chemistry. What piece of information that's usually hanging up in most every science room? Yeah, the periodic table. So we go to the periodic table. So we're going to change grams to moles using our good old friendly molar mass off the periodic table. Sodium hydroxide is a nice one. It's only 40. Pretty much 40.00. So this is a T-chart. Quick conversion. We go from grams to moles using our molar mass. That comes out to, I believe, 0.3 something. Yeah, 0.35 moles of our sodium hydroxide. So now we've got moles and we have liters. We can get concentration. So we take our 0.35 moles of sodium hydroxide, divide that by our half a liter of solution that we made with it. There's our concentration, 0.7 molar. Actually 0.700 with our sig phase. 0.700 molar solution of sodium hydroxide. Any questions about that one? So sometimes you might have to use the molar mass to get the number of moles, because that's how we measure everything in labs. We would be measuring it in grams in order to be able to make these solutions in terms of molarity, because we have to convert that mass into how many moles it is. Next problem, how many moles of sodium hydroxide are in 38 milliliters of a 0.5 molar solution? This is different on a couple of levels. We got milliliters, not liters. That's one issue we've got. The other thing is that all the other problems we've done so far have been calculating the molarity. Now we've got molarity. It's been given to us. Ooh, this can be a little bit trickier. Let's see. We need to find moles. That's what it's asking for in the problem. Find moles. We have the volume. It's 38 milliliters. The other thing we have is the concentration, which is molarity. But remember, molarity is moles per liter. Make sure you get that relationship cemented. Molarity is moles per liter. That'll help you out. So we have that situation where we have a measurement that's really kind of a ratio like that, something per something else. Guess what we get to do with that? Use it as a conversion factor. Yes. Yeah, T-chart. Well, we know we got to change milliliters to liters, so we could go ahead and we can do that right away. So 38 milliliters changed to liters. Move a decimal point 3 places to the left. 0.038. Can we have done that conversion with a T-chart? Sure. Skip that. You know, we can move the decimal point. Now I'm going to take my concentration and I'm going to kind of change that M. I'm going to get rid of the M and make that moles per liter. So I know it's 0.5 moles per 1 liter. It's always 1 liter on the bottom. So I'm going to bring that down here and use that as my conversion factor. Put 1 liter on the bottom and a half a mole on top. 0.5 moles over 1 liter is 0.5 mole. So now my liters will cancel out and I will get how many moles. 0.019 moles of NaOH. Cool. Any questions on that one? Fantastic. So, if we're trying to find something that isn't calculated out to molarity right off the bat, you might have to take that molarity and kind of tweak it a little bit so that you can use it as part of a T-chart to be able to cancel units and get the unit you want. Let's take a look at another example. We're almost done. This time we're looking for volume. We're not looking for how many moles we have, we're looking for volume this time. Volume is what we're searching for. We've got the concentration again, and we're given the number of moles. So the only thing missing is our volume. So we're going to use our molarity again as a conversion factor, but it's going to be different than what we used before because we're trying to find moles. This time we're trying to find our volume in liters. So we start off with our moles, how many moles we have we're given. Then we're going to use our concentration as a conversion factor to switch that out. So I'm going to write it kind of upside down. 0.24 moles are in 1 liter, but I can flip that around. 1 liter of solution contains 0.24 moles. My moles will cancel out now, and I'll have my unit of liters, my volume. So it's kind of written upside down, but that's okay. It's legit. We can do that. Our answer is 0.344 liters. Then you'd end up with something liters, moles squared over liters, and that would just put a 2 there. Those units wouldn't cancel. Okay, moles times moles divided by liters. Dimensional analysis. Those moles cancel, we're good to go. Any questions on that problem? All right, I think we got one more to go. Is that what we got? One more?
Yeah.
One more. All right, so we're going to do one more. This is looking for what mass of sodium, or not sodium, calcium chloride is in 25 milliliters of a 0.375 molar solution. So calcium chloride is our solute. We got a volume, but it's not in liters, it's in milliliters. And we're given the concentration. So the concentration we could use as a conversion, 0.375 moles over 1 liter, or 1 liter over 0.375 moles. So let's start off with our volume. This time we could have put 0.025 liters to start off with, but might as well just put that conversion in there as a T-chart. You can just leave it at, yeah, you could just put 0.025 to start with, and then skip that part. Absolutely. So now I'm going to take my concentration, I'm going to break it up to moles per liter. So milliliters cancel, liters will cancel. There's one more step that I need, because the question isn't looking for how many moles of calcium chloride, it wants to know what mass in terms of grams. So we need one more conversion. We go to the periodic table, add up a calcium and 2 chlorines. Because the other thing they didn't give you in the problem was the formula. Ooh. Usually don't give you that. Calcium's a 2 plus, chlorines a 1 minus, so we need 2 chlorides to combine with 1 calcium. There we go. So you add that up. 1 calcium, 2 chlorines is 111 grams. Do the math. 1.04 grams, that's it. That's all that's in there. It was not a real big concentration, it was a tiny little sample. Not going to be a whole lot though. Any questions about that one? It's about as tricky as it would be. You got to define grams and milliliters, so you don't have liters or moles to start. You got to use those tools we've already learned how to manipulate those to get what we need. All right, last slide is chemistry cat. I stole this one because it used to be chemistry cat would say calculate the molarity of sodium chloride in the tiers on your chemistry test. Very depressing, so I said no. Calculate the molarity of sodium chloride in your tears of joy at being able to understand molarity. Tears of joy.
Joy, happiness.
Italians aren't happy. We don't get it.
Their joy is expressed through your hand.
Does the government run organization?
You know, Daniel, what you don't understand is that people sometimes aren't Italians all the time.
Yeah.
So we have the happiness, right? And we're all
It's different for you,
You probably don't know what it is not to do.
Yes, I
I know, what is this?
Okay, so here's a worksheet. I screwed up. I told the last class this would be due on Friday. I didn't think I had put the due date on, but I guess I did at some point. Great, this is on work. Not do one more.
Yes, So heavy.
Well, we're going to continue working on it tomorrow, so most everybody will probably get it done tomorrow, but
Now I
What does it do?
Air.
we'll make it Friday, so I told you other
Oh,
times.
Friday.
Air is slip, back solvent or solvent.
What's in the air?
Solution.
How are we supposed
I
to
can
know
look at my
these?
notes.
Okay, so at the very top of this worksheet, you've got like a list of different substances or mixtures, and they're looking for like the solvent, the solute. You're not supposed to know all of these. I mean, I don't even know some of these probably when I looked at it. But here's the wonderful thing that you have access to. It's called the internet. Or internet. So you do the first one, you go like just do composition of air. Look at that. Whoa, boom, up pops some information. It says, by volume, dry air contains 78% nitrogen, about 21% oxygen, 0.93 argon, and a really small amount of carbon dioxide. So which one of those would be the solvent? Nitrogen, yeah, it's always the most abundant material is going to be your solvent. So nitrogen is your solvent. Then it says there, give the top 3 solutes, not including water vapor. So next up is oxygen, and then you have argon and carbon dioxide. So you can just use their symbols if you want to. Don't forget nitrogen and oxygen are diatomic those. N2 for nitrogen, O2 for oxygen. Argon is AR.
Wait, so the
Carbon dioxide.
solvent is just the one that has the most?
Yes. So there's one that's going to be really tricky. That's number 4. 50-50 mix of alcohol and water. Is there a solvent?
No.
That's what's tricky with that. You can kind of think of either one of them as being the solvent.
So just write these down.
You just say like either, potatoes, tallow, colloid, colloid.
Gotcha.
What's a solvent?
So you just look those ones up. Look up dental amalgam. That one's going to be kind of interesting. You'd be kind of surprised what the solute is.
Wait, for 4, which one's?
You're putting that in your mouth, but it's okay because it's
Just either?
it's in a solution. It's all good. All right, then we can do like one of the molarity problems down at the bottom. I think saline you had in your notes.
Like carbon water.
So you do number 23 here real quick. Because that's what the other class chose to do. So for number 23, it's asking you what volume is needed to make. So it doesn't specify that it's liters or milliliters. So you could just calculate this as liters. Not to worry about it. Sometimes it might say what volume in milliliters. So you got to always be kind of careful that you read into that. But this one is asking you what volume is needed to make 4.5 molar solution. So we got the concentration that contains 50 grams of ammonium hydroxide. So we're trying to find volume. We've got the concentration. It's 4.5. And I'm going to do something here right away. I always like doing this with molarity problems. I don't like writing the M for molarity. I like breaking it apart so I remember that I've got moles and liters both represented there. So I write moles per liter like that. And then the last piece of information that's on here is you've got a mass of 50 grams of ammonium hydroxide. All right, so I know that my concentration is moles per liter, so really my concentration, my molarity, is moles over liters. So I want to solve for my volume. That means I'm going to need to somehow have my volume of liters would be my molarity, the moles divided by my molarity. So I've got my number of moles. I don't have though. I've got mass though. I can use that to get. The first thing I'm going to have to do is change this to mole. So I go to the periodic table. I add up a nitrogen. There's 5 total hydrogens there and an oxygen. So that's 10, 23, 5. So I go ahead and I calculate that out. Find out how many moles I've got. 50 divided by 35 is about 1 point, I'm going to keep a couple of things here, 1.429. That's how many moles of ammonium hydroxide I have. So now I'm going to use my molarity as a conversion factor. I'm going to want the mole part to be down on the bottom, so 4.5 moles per 1 liter. 1 liter will go on top. Moles will cancel out. That should do it. So my 1.429 divided by 4.5. That equals. And it did say to change that to milliliters, so I'm just going to leave it like that. 0.317 liters. Fast is almost what it's. Oh,